The amazing astrophysicist Cecilia Payne-Gaposchkin worked out that stars are mostly hydrogen and helium gas, not huge lumps of burning coal, as all the distinguished male astronomers thought at the time. After a while, Arthur Eddington suggested that the hydrogen gas couldn't be burning like normal, as there's no oxygen in space for the fire. But another process called fusion could be happening. In fusion, hydrogen nucleuses are mashed together to make helium. That's why there's hydrogen and helium in stars. Masses and masses of energy comes out too, and this is starlight. The hydrogen nucleuses each have a proton, so each are positive, and charges that are the same. In other words, positive and positive really hate to be pushed together. There's lots of massively repelling force. So hydrogen fusing is immensely hard. Stars have such enormous gravity that these hydrogens just get mashed together anyway, by the gravity. Deal with it, girlfriend, as they say in Luxembourg. Here on Earth, we can't create a local area of enormous gravity to do fusion in the way stars do it, so instead we just have to slam the protons together using temperatures 20 times hotter than the Sun, so they fuse into each other and make helium. Making small stars on Earth is difficult because of these incredible temperatures. If you put anything that hot in a container, the container vaporizes, which is not completely ideal. So we rip a few electrons off the hydrogen gas so it becomes a plasma gas, and magnets can suspend the plasma gas so it doesn't actually touch the container sides. Then fusion can happen, releasing far more energy even than fission, no radioactive waste, no carbon dioxide. With the downside being that fusion is an incredibly challenging engineering feat to make happen. That said, a number of companies are getting pretty close. Going back to decay, the regular kind of radioactivity we've talked about loads before. In the 1920s, shortly after radioactive materials had been discovered, radioactive materials started being put in a lot of expensive consumer products to help give people energy, or so it was thought. You could eat radioactive butter, drink radioactive water, smoke radioactive cigarettes, and put on radioactive face cream. What was there not to love? Well, a lot of people started dying and getting horrible radiation burns, so there was that. Physicists decided that it was time we thought about the effects that this radiation has on living things, and this idea was called the dose. There are 3 measures of dose. The basic one is called absorbed dose, then equivalent dose is a bit more sophisticated, and finally, equivalent dose rate is the most useful. We will start with the simplest, which is absorbed dose. Absorbed dose, D, is the energy that you get from being hit by radiation, divided by your mass. A big sumo wrestler will be less affected by a dose of radiation than a baby, because the mass, m, on the bottom of the fraction, will be ginormous, so the dose D will turn out small. D equals E over, or divided by, m, on the formula sheet. D, absorbed dose, is measured in grays. Gray was the person who suggested back in the 1920s that children using X-ray machines as toys, taking as many X-rays of themselves as they wanted. Maybe wasn't a great idea. 1 millijoule of radiation is absorbed by 0.5 kilograms of tissue. Calculate the absorbed dose it receives. Shopping list. Remember that prefix. Formula, numbers in, final answer gets units. Calculate the energy a 60 kilograms person received from radiation, if they are exposed to 7,000 micrograys. Shopping list. Remember that prefix. Formula. Numbers in. Triangle if you get stuck. Triangle says take the D number and times it by the M number. Final answer gets units. Equivalent dose takes into account what type of radiation you are hit with. So equivalent dose is absorbed dose, which we know about already, multiplied by something called a weighting factor. The weighting factor is a number that is unique to the type of radiation. So you look up the radiation weighting factor on the datasheet, then put it into the formula. On the formula sheet, equivalent dose is shortened to capital H, which doesn't make the most sense, but we just have to kind of get used to that. Equivalent dose is measured in sieverts, capital S, lowercase v, for short. Absorbed dose is in grays, as before. Weighting factor doesn't have units, and again, you usually have to look this up on the datasheet. An alpha-emitting material was swallowed by a fish, giving it an equivalent dose of 5 microsieverts. Calculate the absorbed dose the fish received. Shopping list. Remember that prefix. Weighting factor for alpha has been got from the datasheet. Formula. Numbers in. Triangle if you get stuck. Triangle says take the absorbed dose H, and divide it by the weighting factor W. Final answer gets units. Finally, and this is the last part of the nuclear topic, you've done well. The best, most useful measure of dose is called the equivalent dose rate. This takes the equivalent dose, that we know already, and say, actually, time matters too. If you get a big dose of radiation, but it's spread over like a few years, that might be barely noticeable. But if you get that big dose of radiation in a few seconds, you'd probably end up with very bad radiation sickness. Equivalent dose rate is H with a dot above it. Equivalent dose rate, then, is equivalent dose, H, divided by time, little t. In terms of units, the question quite often asks you to give your equivalent dose rate answer in sieverts per hour, or sieverts per minute. So if it asks you this, then you'd leave time in hours, or in minutes, too. This is about the only occasion we don't automatically put time into seconds. A radioactive source exposes a worker to an equivalent dose of 80 millisieverts. If this is over a time of 2 hours, calculate the equivalent dose rate in millisieverts per hour. Shopping list. Normally, we'd swap the milli prefix for times 10 to the power -3, and we'd turn the 2 hours into seconds. But here, the question has asked us for the answer in millisieverts per hour. So we'll just leave those units as they are, for once. Formula. Numbers in, final answer gets units. We're done. Good job, Batman.